Where is Lorenzo? Where is Gaia? Hold on a minute. Ah, there you are. So welcome back to the lab. Have you had fun so far?
Yeah.
Fantastic. So we are now going to learn about why we are in space right now and yet we are not floating around in the spacecraft.
Okay.
That has all to do with some very famous scientists. Have you heard of Isaac Newton before?
No.
You have. Aha, we'll learn about Isaac Newton. Have you heard of someone called Galileo Galilei? You have? We will learn.
I heard of Galileo.
Yeah, fantastic. We're going to learn all about these two scientists. We're going to learn about what they taught us, about how the force of gravity works. Are you ready?
Yeah.
Fantastic. So,
An orange.
an orange. And let's take,
Why is there a hole in it?
no, good question. A duck. Okay, simple question to start with. Which one is heavier? The orange. Can you test? Can you hold them both and find out for yourselves which one feels heavier?
Yeah.
Easy?
Orange.
Okay, perfect. So, there was once a long time ago, someone who came from ancient Greece called Aristotle. And Aristotle thought that the heavier something is, the faster it will fall. And the lighter something is, the slower it will fall. Kind of makes sense?
Yeah.
However, he lived in a time before people did experiments, which of course is what we're doing all the time up here in space. Now, we have to then fast forward to Galileo Galilei. Galileo, he was sort of like one of the first proper scientists because he liked to design actual experiments to prove ideas. So he took Aristotle's idea of something heavy and something light. And he got to thinking, is that really how things work? Is it to do with how heavy you are and that's how fast you fall? So he designed an experiment. He took something very, very light and something very, very heavy, and he simply dropped them at the same exact time and watched to see which one hit the ground first. So we take a heavy thing and a light thing, hold them up high at about the same distance from the ground. Would you say the duck and the orange are about the same distance from the table? Yeah. Yeah? Shall I move one up and one down?
The duck a bit higher.
Yeah, about there. Perfect. Okay. Yep.
Yeah.
Looks good?
Yeah.
Okay. So I'm going to drop these. Which one do you think is going to hit the ground first?
The duck.
The duck? What do you think, Lorenzo?
Orange.
Duck or the orange? Okay. There are some other options too. Will they come together?
No.
Do you reckon if when I let go, they will hit the ceiling instead?
No.
Will they bounce off the table, hit each other and turn into a banana?
No.
Hopefully not. Okay, right, I'll drop them. Let's see what happens. So you said orange first, and you said duck first. Okay, let's see. 3, 2, 1. What happened? They both hit the ground at the same time. Isn't that strange? Even though they are different weights, well done, they both hit the ground at the same time, every time. Now that's all to do with the force that's pulling them. Which is the force that's pulling these two things to the ground? Gravity. Fantastic. And now we are up in space, but down on the Earth, what is pulling things? There is gravity, of course, and it's the Earth itself that's pulling these objects down. And the Earth is pulling everything with the same force. Now, heavier things, that's right, are being pulled a little more than light things. However, because it's so heavy, it is resisting that force more than the light thing. The light thing is easy to move side to side. The heavy thing takes more energy to move, okay? So this sort of balances out. The Earth is pulling this harder. Have a go. That's right. The Earth is pulling this more, but it's resisting that pull more, and that is being pulled less, but it is lighter, so it's resisting it less, so they end up falling at exactly the same way.
But it depends on the shape, because the circle is better.
I'm really glad you mentioned shape, because in Galileo's day, there were people who asked another question. Okay, so you have a heavy thing and a light thing, and yes, in this instance, they fall at the same speed. But what about something that's really light? What about like a feather? A feather would be much lighter than this duck,
Yeah,
right?
it goes way slower.
And that does go way slower. But Galileo said it's not to do with the weight, or if you like, the mass of that feather. It's to do with something else. And it's because, what are these two things falling through? Nothing?
Through air.
That's right, they're falling through the air. That's right, well done. They're falling right through the air. So if you take, for example, a feather, which is all broad and fluffy, it's going to fall through the air, and the air has all that surface to push against and slow the feather down as it falls. Whereas the orange has only this area here. So the air can't push up against it as much, so it falls faster. And the same with the duck, that's right. But if we hammered this duck out and made it really flat, so if we take, can you find some tissue down here? Let's say we squash this duck down into a flat shape like this here. Now, have a go. You can see, that's it. It flutters and falls because the air is stopping it. So, that's right, that's right. So Galileo knew that, of course, that is still the same thing. They still should be falling at the same rate. It's just air is getting in the way and slowing down the paper. So he made another experiment. And this was an experiment that took place up here.
Brain.
In your brain. A thought experiment. Can you say that?
Thought experiment.
Very good. And in this thought experiment, he took a hammer, something heavy, and a feather, something very light. And in his thought experiment, because he got to imagine this, he could do this experiment wherever he wanted. So he thought, if you went to a place where there was no air at all, and you dropped a feather and a hammer at the same time, there's no air, what do you think would happen? Go down straight. And would they hit the ground at the same time, do you think? Yeah, that's right, they would, because there's no air to slow the feather.
Like, go in space.
Well, he thought, I need somewhere with no air, but with a surface to stand on. And he thought of one place.
On the moon.
Bingo. Well done, on the moon. He thought, my thought experiment can take place up on the moon. And what's amazing about this experiment is, it has actually been done in real life. So when astronauts went to the moon a long time ago,
Wait, was it the first one?
it was actually about 3 missions after the first person who went to the moon. So there are lots of people who went to the moon since that first one, since Neil Armstrong went with Buzz Aldrin. After him, someone brought a hammer and a feather, and they did this very same experiment on the surface of the moon, and they proved Galileo correct about 500 years after his experiment. How cool is that? Really cool, really cool. Building on what we've learned, we could do all sorts of experiments. But I thought the best one is all to do with how we keep ourselves balanced. Our bodies are always fighting against gravity trying to pull us down. Have either of you fallen over before?
Yeah.
Yeah? You know what? That happens. That's true. I've fallen over a whole bunch of times. I've got scars on my elbows and my knees from falling over. Gravity is always trying to pull us down. And when we lose balance, we fall over. Simple as that. Now, losing balance is all to do with your center of gravity. Have you heard of that before? So every object has a center of gravity. It's the area where the Earth is pulling the strongest on this object. Now, the center of gravity for this orange, because it's more or less a sphere, the center is going to be right in the middle. So that's why it's fairly stable. You can roll it around. It doesn't really move strangely.
All balls are spheres.
Absolutely right. So their center of gravity is always going to be in the middle. What about a human? Now, we are a kind of funny shaped thing. Where do you think our center is? Up here? Here?
Right. Here, maybe?
That's about right. It's about where your belly button is, roughly. However, we have legs that we walk around with, of course. We move our arms too. And as we do this, our center of gravity can move. And sometimes it will move outside of your body. Now, you can't see your center of gravity, but the Earth knows where it is. The Earth is pulling towards it. So if it moves out of your body, you will fall into it. You will turn around your center of gravity and fall into it. So every time you've fallen over, it's because your center of gravity has moved out of your body in some direction, and you have fallen over onto it, and that's what's made you fall over. So I'm going to take some other strange objects here. What is this?
That's a spoon.
That's a spoon. And we're going to try
Wooden spoon.
a wooden spoon, to be precise. Very good. We're going to try to balance this on the tips
An orange.
of our fingers like this. Now, do you think that's possible? If I let go with my thumb, will it stay on my fingertip?
No.
Of course not. Because its center of gravity is somewhere in the middle. And you will never, you will never be able to balance it by the tip. That's right. The way to find the balancing point for it, the center of gravity, there is just one way. And I can show you. You need not one finger, but two, Lorenzo, like this. Take the spoon, one on each side. and move your fingers underneath it until they come together. Can you do that?
Yeah.
Mm-hmm. Yep, starting under. Move them together. And you'll find the middle. Did you see what I did? That's it. And you'll find the center by moving them together. That's right, that's it. So as you do that, it will slowly find the very center. That's the center of the spoon's gravity, about there. But we want to balance it on the tip, right here. That's what we want to do. And we need to know how that's possible. So we actually need to add some things to this.
Oh,
What to do?
I know how.
Okay, what do you think?
Add some blue tack.
We could add blue tack to one end to move the center of gravity closer to where our finger is, absolutely. Or we can add what's called counterweights to it. So we can balance it not just on the tip of our finger, but I think we can even do this on the end of our nose as well. Yeah. So to do that, I'm going to give you guys one of these each. What have you got here in front of you? Mm-hmm. You need 1, 2. 2 each. Now we're not going to stick these to our noses or to the spoon. We're going to stick them to these over here. 1. Pipe cleaners. Pipe cleaners. Okay. There we go. So what you need to do is, I'll show you very quickly on this example, I'll pass it over to you. To find a way to get this to balance on our fingers, we need to add these things called counterweights, which are our pegs here. And the first step.
Point.
Wrap this around. Just behind, that's it, on the center. Add your pegs to either side. One down here and one on the other side. Can you do that? Add one peg over here and one peg over here. Can you do that? Great. Other peg on the other side. Sort of like your spoon has 2 arms with peg hands up. Yeah?
Like
Good.
yeah. Toys.
Mm-hmm. So we'll start, this is the first,
These are 4.
yeah, this is the first part of our design. Let's see if it balances now. Hold your finger like this. Let's see if we can balance it on the single finger. Not yet. We need to do some changes. Not yet. We'll need to do some changes. So strengthen by adding another pipe cleaner. So to do this, remove your first pipe cleaner, take your pegs off, and then can you wrap the pipe cleaners together? Can you do that? I'll show you like this. That'll make it stronger, so you can kind of twist them, put them side by side. Twist them together. I'll give you a hand if you find it tricky. So that now should be twice as strong. Can you put the pegs on the end again, just like you did before? This is looking good. What you need to do is you need to get your counterweights underneath where the spoon touches your finger, okay? If you can hold those down underneath, about where the spoon touches your finger. Getting it? Try and practice. Even try this way. Ah.
This.
There we
What?
If you hold your finger out, we'll see if I can pass it over to your finger.
Oh, your ring on your side.
Yeah, there you go. Well done. Let's see over here. See if I can get under your finger. I think you've nearly got it. Hold your finger like this, nice and firm your finger. That's it. That's good. Yeah. Excellent. Well done. Very good. Hey, well done. I said earlier that we were going to answer the question as to why, if we're in space right now, why aren't we floating around inside the spaceship? And the answer to that is very simple. It's because we are moving right now through space. Our spaceship at the moment is traveling past the moon, okay? So we are moving right now through space. If I stop the spaceship and we all of a sudden stopped in space, we would start to float. So why is it?
Because
Why do you
we're
think?
maybe moving fast.
We're moving fast and we're getting faster all the time. We are accelerating through space. We are moving faster and faster and faster. So,
If I spin this car.
okay, for example, you are onto something very, very good there, Lorenzo. I really like it. So this is a nice way of explaining why we are stuck down to the ground here at the moment. So we are accelerating in this direction. We're not going this way. We're not going backwards. Left or right. We're actually going through space that way. The front of our spaceship is pointing like that. So we are being pinned down here because we are accelerating in the opposite direction.
Up there.
That's right. So this sort of gives us something that feels a lot like gravity. So if I pick up a rubber duck and drop it, it seems like gravity's pulling it down. But here on the spaceship, it's because we are moving in that direction, and this duck actually is not moving to the ground. Do you know what's happening instead?
What?
The table with the rocket underneath it is moving up.
With the water.
Right. So for this experiment was done by another very famous scientist called Isaac Newton. And I asked you if you knew about him earlier on. So Isaac Newton, he had an idea as to why the moon. That's right. So he had a very good theory of what gravity is and why we have it. And he wanted to ask the question, why does the moon, A, not fly off into space and leave us, and B, more scary, why doesn't the moon come crashing down to the Earth? The moon is high up in space, and if I drop an apple, for example, it will come down to the Earth. And the apple is up away from the Earth when I drop it. Why doesn't the moon come down too? Or why doesn't the moon fly away? Well, the moon is being pulled by the Earth right now. The Earth is pulling the moon towards the Earth. However, so the Earth is pulling the moon towards itself. However, the moon is also trying to move itself. So if the Earth, if you make a fist like this, that's the Earth. And Lorenzo, your little fist here, that is the moon. So the Earth is pulling the moon toward, but luckily this doesn't happen because the moon wants to travel this way. So the moon is caught by the Earth and it, whoa, that's it, spins around it. That's it, fantastic. So Isaac Newton had a way of explaining that. Take some water, place it in our cup.
Oh, the one.
Right, so
This
if
is
I turn this cup
dangerous.
upside down over my head, what will happen?
Do it over your head.
Right, exactly, well I will. The water will fall out. But if we spin it on these beads and we turn this cup around by spinning it, the water is pushed to the bottom of the cup by this motion. So we can think of the cup as the moon, my hand as the Earth, and these strings as the force of gravity pulling the moon towards. And as I swing it, that is the moon's motion it's trying to go. So if I give it a spin, let's see if we can keep the water in the cup. Are you ready?
Yeah.
Let's see. Whoa! Can you see how it stays inside? But this was Isaac Newton's idea, that the moon is held to us by gravity. But because it's moving, it is constantly kept in this pattern that we call an orbit. Can you say that? An orbit. Fantastic.
Like
the moon is orbiting the Earth.
Blue thing around the Earth.
That's right. That's right. So the moon is always orbiting the Earth, and we are always orbiting the sun. Fantastic. So
Yeah.
another experiment. We are up in space. We've talked about gravity. Absolutely. A syringe. Give it a push. Fantastic. So
A bit of
our syringe here is a very interesting tool because it can teach us a little bit about, I take a little cup of water here. It can teach us a little bit about water. Now water, we've looked at water today. Water is a liquid, but it's not always a liquid. So when water completely freezes, we call it something called ice. That's right. And if it boils, it turns into a gas, which we call steam. And the clouds are made out of that same stuff. Now, to turn a liquid water into a gas, what do we have to change? Change the temperature, make it hotter. And then to turn it into ice, we need to
Make it colder.
make it colder. Fantastic. Now, at the moment, we have fairly cold water.
But like in my class last year, we like tried the experiment like when you like put like the bottle in the freezer, but it didn't freeze.
Aha,
The
not enough
other
time?
classes froze.
Okay, yeah, okay. Well, we're going to try and do the opposite. We're going to try to boil this water. Now, there's different ways of boiling water. We can boil water by heating it up, but I only have a syringe.
Eating.
We can heat it. I've only got a syringe, so I
I thought you
can't
said
heat it. No, heating. So we can't heat it. We've got nothing to heat it with, but I've got a syringe. And I'm going to boil it without heating it. There's another way to do that. So I'm going to...
Just blow hot water on it.
Well, I've got no hot water around. All I've got is a syringe, now with some water in it. Now, to get this to boil at this cold temperature,
I think
what do you think I can do?
put it like next to a light.
I could do. I could find something that's warm and put it there. But let's say I didn't have any of that. All I had was a syringe
And wood.
and a thumb.
Bang.
If I put my thumb on the top here and I pull this plunger down, I will create in here an area that looks like it's full of air, but it's actually full of really nothing. What we call a vacuum. Can you say that?
Vacuum.
Vacuum.
No.
It's sort of like a vacuum cleaner. That's exactly how they work. Very good. So when I pull this down, have a look inside and you might see a few bubbles forming. And as you see those bubbles, it's not hot, but it is boiling.
This is
So have a look just inside here. Yeah, I'll take this to one side and have a look inside here. Okay, I'll turn it this way. Can you see those bubbles?
Yeah.
Yeah? Can you see that? That's boiling water in there, believe it or not. Does it feel hot?
Yeah.
That's because we have made it boil, and we come back again, look, by reducing the pressure on the water. Okay, I hope you enjoyed today's experiments up on the spaceship. Did you have fun today?
Yeah!
Fantastic.
Don't forget, keep exploring, keep learning, and keep having fun. See you at the next adventure!
Yeah!